2-4. We're going to start talking about variation and standard deviation. Words you may have heard before, but maybe not 100% sure what they meant. And as we go through this class, hopefully that becomes much more clear. Range, I think you all know how to take care of range. That's not exactly the most difficult part of this particular day, but basically take the minus, yeah, pretty much that's what you got to do. And as it says here, the difference, which is subtraction, between the maximum and minimum entries in a set. So no big deal there. And what I'll do here is I'll just say this is a corporation that hired 10 graduates. I think 10's a nice small number to deal with as far as this. It's, you know, we don't need to be looking at 100 bits of data here. The starting salaries for each are as follows. Note that the salaries are in thousands of dollars. You will find out real quick as we go through this. We're going to be using these numbers a lot today. Why we don't have 41,000, 38,000, and 39,000 written. You will find out real quick. Okay. Here it says identify the minimum, maximum, mean, and range. So why don't you take a few minutes to take care of that? It shouldn't take you too long. All right. So again, hopefully it took a few seconds to do that. The minimum. What is it? 37? All right. The maximum. 47. Probably range is the next one to do then, right? Because you're going to take basically 47 minus 37 and divide it by 1. Very good. I'm seeing if you're paying attention there. All right. So all we got to do is take that, and it equals 10. Yeah, it says above, or you could just say, you know 10,000 and all that if you want. Yeah, 47,000, 37,000. And the mean. What is it? So 41.5, which translates into 41,500. Now, here's the question. Should I label 41.5 as mu or as x bar? What's the difference between the two? Let's see if you remember. Because x bar is used when you're talking about sample. Mu is when you're talking about the hired 10 graduates. Starting salaries for each are. So this is mu. So basically to make mu, just make a u and then just make it look weird. Yeah, that's good mu. All right, very good. So yeah, that's the population because we have all 10. Yeah, if I had only given you 8, well, then you would have said, well, it's x bar, right? Yeah, they'd have to say something like that, yeah, so that you knew that wasn't all of them. And I should probably actually make that more clear. Hired only 10 graduates or something like that. Then you would know that it's all 10, yeah. All right, so that's not that hard, right? That's pretty easy. You notice I didn't ask for median, okay? Because when you're talking variation and talking deviation, you're not going to use median. And it goes back to that thing I showed you the other day on the board that if you have median, there's more than one answer sometimes. And we want 1. Okay? And eventually that's what we want is 1. And it's going to take us a while to get to what we're actually using this information for, but you trust me, we'll get there. Oops. Where's my next word? I didn't put deviation on there? Well, there it is. It's just hiding. Oh boy. Now it's just being ornery. Well, you can leave that one on there, it doesn't matter. So deviation. I didn't expect you to know this one. So the difference between an entry and the mean mu of the data. And again, this is of a population, is what we're talking about here. Difference between an entry and the mean mu. Obviously, if it was a sample, we'd say the difference between the entry and the mean x bar. And as you see there, basically it's just x minus mu. That's all deviation is. Man, things big. Where's that little guy? There he is. Can't get to him, huh? There. You already know the answer, but that'll get the once we get there. All right. So what you need to do here is notice here are the salaries, right? I put them right there. And apparently this little sigma x equals 415. What does that mean? Yeah, the sum, right? So a lot, $415,000. All right. So the deviation, we're going to take x minus mu.
Samantha Holler to the high school office. Samantha Holler to the high school office.
So we're going to do that, correct? Do you really, this is x minus mu for the first entry, right? Because you just told me that mu was 41.5. You just figured that out, right, for this data? And so you have to subtract, that answer is negative. Negative 0.5, right, in this case? Next one's also going to be negative. It's going to be negative 3.5. Okay, and why don't you go ahead and finish those up quick? They're pretty straightforward numbers. And now you're kind of seeing why, one of the reasons we're taking those thousands off, but there is another reason that's coming up pretty soon here. Again, this is deviation, not standard deviation, just deviation. There's a big difference. And I think we're all capable of filling that in. So there you go. There's the rest for you. I don't think subtracting is going to be the most difficult thing for us in the world, right? As you notice, though, there are some negative and some positive. That's a problem. That's how far it is from the mean, right? And that makes sense that some should be positive and some negative, right? Because the mean is supposed to be, that average, right? So does it make sense that if you actually add them all up, that it should be 0? If you compare it to the average, does it make sense that it's 0? Yeah. So basically, if we try and calculate anything and we just use deviation, the negatives cancel out the positives, right? If we set it to the mean? Well, that's a problem. So basically, we did all this work and we've gotten nowhere. So then we have to get rid of negatives somehow. We have two options. We can take absolute value, which is more your median, or we can square it, right? That's the two ways you can get rid of negatives. But once we square, we're going to have to eventually square root, right? But why don't we use absolute value again? It could create many answers. And in the end, how many do we want? One best answer. Okay, so that's why we're going to go with the squared idea. Okay, any questions where anything from that table came from? On we go. We're going to talk about variance now and population standard deviation. How much it varies? Well, variance. Oops, wrong one. Well, you can just look at them both, I suppose. It's the mean of the squares of the deviation of a population data set. What some people do is they just kind of write the formula down. That little A-looking thing is actually also sigma, this one right here. Just lowercase. Okay. The reason they wanted to do that is they already had sigma there. So to put sigma in both locations would be confusing. Okay. So basically what they're saying is let's square all of them, right? That's what it's saying. Let's take x minus mu and square them. Each particular one, do you agree that takes care of negatives? They all become positive, correct? But much larger than they're supposed to be, right? And then that sigma says to take all of those n, add them up, and then divide by n. What's n again? The number, yeah. What's the number of the population? In our example, it's 10, right? In our example, but obviously n can change depending on your problem. So do you agree that this would take care of all negatives, right? But is variance a very helpful number? Does that help me determine anything about the difference between the numbers? Not really, because it's been squared. So do you agree that distorts things big time? So the variance itself is not very helpful. So what do you suppose we're going to do to it? We're going to square root it. And they call that the standard deviation. All right? The square root of the population. They got to love that definition, right? It's the square root of the population variance. Or, as you can see, all I did there is it's just sigma, lowercase, or the square root of that. And again, you use sigma when talking about population. Okay? You use something slightly different when talking about sample. We're just talking about population today. Because let's face it, this is the number we want anyways, the deviation of a population. But the problem is, what's the problem with population? Some of them are big or even unattainable. Okay, we had 10. That's attainable. All right. So basically, you notice all I did was basically took the square root. Well, there you go. And obviously, if I take the square root of this right there, I'm left with that, which is really what we want. But to do this by hand, with even 100 bits of 100 entries, take you forever. We're just going to do it with 10. All right. So for those of you that were very clever and flipped your page over, you realize you already had all these numbers. But now we have to take the squares. And this is a table that's all very common ways of doing that. So you're telling me if I take negative 0.5 and square it, that it's going to become positive? Now can you possibly see why we're not using 41,000? Because when you square it, it's going to get just ridiculous. All right. And so we figured, well, it's the same numbers, right? So we might as well do it this way. So you take negative 0.5 and square it, though, and it actually gets positive, but actually when you square it, it actually gets a little bit smaller. And for those that maybe don't know, it's 0.25. And I'll have you do just a couple more on your own, and then we'll be done with that, because I think we can all square, because we already have the number, we just got to square it, right? I mean, and really, you're smart enough that, do you even really have to type the negative in on your calculator? No, because you know it should become positive, right? So just take 3.5 and square it, and so forth and so on. And then now, one thing we know for a fact is if I start adding these all together, am I going to get 0 now? No. And so we temporarily solved the problem. Yes, but unfortunately, we've created another one. So again, I think you can all square numbers, so go ahead and just write those down. They're right there. And if you want to put more lines in there, that's fine as well. And once you do that, figure out sigma of x minus mu squared. All right, so there's your numbers. Those are the squares. And so what is the summation or sigma of that? What'd you get? That's what I got. So what is that number? What does that tell us? Well, not a whole lot. That tells us that if I took x minus mu and squared it and add them all up, that's what I get. That's what it tells me. So how are we going to use it? Do you agree that's basically the sum of the variance, right? So the variance is just variance here. You have to take the sum, which is right here on the numerator, and divide by n, which in this case is 10, right? So variance here is 8.85. But again, that number in itself really doesn't tell us a whole lot either. Okay, because that's still a squared number, right? And you don't have to write all that. That's just from the definition. You can just write that, sigma squared, that, lowercase sigma squared is 8.85. You don't want to do the other one again because there's then too many sigmas in the problem. But sigma still means a sum, right? You agree sigma squared is still also a sum, so that's why we can use it. So to find the standard deviation, what do I got to do to 8.85? Yeah, square root that thing. That's right. Approximately 2.97. Or we could probably even say approximately 3, right? But we've done all this work, we might as well at least go out a couple decimals, right? So who can tell me what that means? It's a whole lot of work we just did. If you can't really tell me what it means, it doesn't really matter. Nope. Nice try, though. Nope. Basically what it means is if I were to pick a salary at random, I would expect that it would deviate from the mean by approximately $3,000. That's what I would expect would happen. Is that what we're guaranteeing is going to happen? No. But that's what we would expect. Again, if you just picked one of the salaries at random, we would expect that it would vary by about 3,000. So if I did it without looking and I picked, say, that one right there, 39,000, does that vary from the mean by approximately 3,000? That's what I would expect to have happen. Is it pretty close? Remember, what's the mean again? 41.5, right? And then you just do it again. Okay. Obviously, if I pick some, it's not going to work, right? But that's what we're saying. We're expecting that to happen. There's no guarantee that it will, but that's what we're expecting. Because, and you're going to learn this later in the chapter, about 2/3 of the data, approximately, would be expected to be within one standard deviation either way of the mean. Here comes your bell-shaped curve. All right? That's how we would expect about 67 to 68% to fall within one standard deviation either way. That's a good chunk of the data, don't you think? Okay, and then obviously there's more on the way out, but you're going to learn that. But that's why we do standard deviation. Again, why do we go through all that business, all this squaring and adding and all this stuff? It's because if we don't, we're just going to sit there looking at that 0 every time we do this. And we're going to get absolutely nowhere every time. Okay? Basically, that's saying I would pick the mean every time, which obviously that's not true, right? I mean, I'm not going to sit here every time it's going to be 0 difference. I don't think so. And so we had to get rid of those negatives, because otherwise they're just canceling out right now, right? I mean, so what's the point there? We had to get rid of those negatives, and we chose squaring, remember, because we're going to get down to one answer later on, okay? And so we square them, we add them together, divide by how many we had, and boom, there it is. Okay, yes? It's not going to happen. If you do the problem right, you're going to be staring at that 0. All right? If you calculated your mean right, that's the whole idea of the mean. Because you have to get that so you can square it. You have to get the deviation so you can square it. Well, let's say, if you take just the deviation and square it, you get variance. If you turn around and take the square root of that, you get standard deviation. No. Right. Each one of these this is the sum of the deviations down at the bottom, which is always going to be. In fact, let's face it. Is it possible that the mean is actually one of the values? Yeah. Then your deviation, there's obviously 0. You turn around and square it, it's still 0. But it is possible to get a deviation of a particular entry to be 0. But overall, I'm telling you, it's going to be 0. But so that's why we turn around. We say, okay, let's take deviation and square it. Basically, if I add all those up, I get variance. Okay. All right. And then if I turn around and basically take the square root, we're to standard deviation, which is way better than just deviation because we know the sum of that. All right.